Okay, so welcome back for this second part of the first session. The session is about the ferroelectric material and devices. The next speaker is Johannes Ocker from Ferroelectric Memory Company in Dresden. So FMC is partner of our Intersect project, and today Johannes is going to talk about the interplay between polarization switching and charge trapping in ferroelectric field effect transistor.
Thank you.
Johannes, please.
Sorry. All right. Thanks for the introduction. And yes, we heard before from Sven and also from Stefan. There's lots of interaction going on between the trapping and the switching. So within the project of Intersect, we try to further clarify that with the help of Ginestra, with simulation tools, to figure out what is really going on, because you kind of need to have some reference in terms of simulation that gives you help in guiding what is actually possible from a physics perspective and what is not, because otherwise, you can make up theories and it's trapping or not, but in the end, you have to kind of get it in a quantitative way. All right. So I will start with the ferroelectric hysteresis, which is probably the most fundamental part that you can actually sense in a ferroelectric memory. And already there you can see lots of different effects that can tell you what is actually going on in your sample. And then I will go over and look really at the ferroelectric switching and the trapping in the ferroelectric, and what really happens once, or what we think happens if we program into a low conductance state and a high conductance state. And at the end, I will talk a little bit about what that means for an actual ferroelectric memory cell that you want to commercialize, because these trapping effects, they are kind of parasitic, so you actually don't want them. And you have to, if you cannot tackle them by process or by designing them out, you have to tackle them in some other ways. And for example, I give this example with how we deal with them in terms of algorithms. So there's some way to, by applying special sequence of electrical signals, where you can faster detrap them and also tailor that for every individual cell, because there's also some variability in these FeFET cells, as Sven said before. All right, so this is basically the introduction. I don't know if we have to repeat that, because Sven talked a lot about that. So this is the TEM, image of the ferroelectric FET. So yeah, you have the silicon dioxide, and you have the ferroelectric layer here, and then the titanium nitride on top. And this is the poly plug of this transistor. And here you have a source and a drain. And now you can switch here in this ferroelectric high K. You can switch the polarization up or down. We call this program and erase. And depending on if you put it upwards or downwards, in this case, for example, here, there's electrons in the channel, and you can conduct current through this transistor. And we call this the program state, and then there's the erase state, where this silicon surface is in accumulation, and then the transistor draws no current, and then you can have two states, one conductive state and one non-conductive state. Okay, and you can see this here as the IDVGs, we call them the transfer characteristic of the transistor. And yeah, basically the trapping, it will modulate this two states here. It will either close them or completely, for example, shift up the low VT above the low conductance state above the high conductance state. And then you actually don't have a memory window anymore, so there's nothing you can actually sense. All right, so but let's first take a step back and look at the MFM, so the capacitor only structure. So you have a top electrode and you have a bottom electrode. And if you want to switch then the ferroelectric, you usually apply this triangular signal and you measure the displacement current of the sample. And if you do that, so if you go from in this first triangular go up, so you go up here, you get this first little switching peak. This is because in the simulation it assumes that one half of the domain is up and the other is down. And so you switch one part of it such that all are aligned, and then you go back and you get this large switching peak from switching everything and switching all the dipoles in the opposite direction. And then if you integrate this, you get this polarization hysteresis. All right. And this is how it looks for the MFM. So this is pretty standard, I would say. We just took the Breisach model in the Ginestra and simulated this. And now if we look at it, how does this look like for a FeFET transistor? So it looks like this. So this is the same voltage applied, just we changed out the structure. We added here the silicon dioxide interface layer, and then we simulated also with the ferroelectric Breisach model the hysteresis. And so you can see here, I can maybe switch back and forth, that the polarization you can actually stabilize here, and this system is very low. So at 0 volt, this is the x-axis is the top voltage, you can stabilize only about 2 microcoulomb. And this is because when you sweep up, there is some depolarization field which forms due to the switching of these dipoles, which, it tries to switch back the dipoles. And this is because of this interlayer here. And so basically you can sweep up here and sweep down, and during the down sweep on this flank, it already starts to depolarize again. And this comes from this depolarization field. So once you put in some dielectric layer, it's very difficult to really stabilize the full polarization. Okay, this is again, this depolarization field is again shown here. This is the same hysteresis, just a little bit zoomed in. And this is here the band diagram of the structure with ferroelectricity, so here, and without ferroelectricity. So this is the silicon dioxide, and this is the ferroelectric layer with here, a sheet charge, a positive sheet charge here, and a negative sheet charge here. And you can see that with ferroelectricity, with these dipoles switch, the field over this transistor would be much lower than if you don't have any ferroelectricity. And this is kind of this depolarization field that makes it impossible to fully switch the ferroelectric. Okay. So there's also one thing which we actually didn't discuss, is that here in the current voltage characteristic of this transistor, you can see here, and this is all assuming no traps, you can see that there's a huge amount of leakage current. And this leakage current, it comes basically from the polarization. So you switch the polarization like this, and this reduces the field over the ferroelectric and increases the field over the silicon dioxide, and then you get a massive amount of current. And this is also what you use in the FTJ that Stefan showed to make 2 different states in the FTJ. All right, so let's compare this with the theory and the experiment. So this is the theoretical curve we get out of Ginestra without any traps. So you can see there's basically no peaks, so we would expect some traps or anything, some polarization peaks here and some polarization peak here. But in the theory, there's actually nothing there because of this depolarization field. But in the experiment, you see very significant switching peaks, and you can basically fully polarize the ferroelectric transistor. So obviously, if we just take the standard model of ferroelectricity and assume no traps, we have a very difficult time to to understand this experimental data. Okay, so, and what you can also see though in this, if you take a closer look in this simulation here, is that if you sweep from negative voltages, and then since the FeFET in itself is still an MOS capacitor, so the silicon, it goes from accumulation to depletion and inversion, and you can also see in this displacement current of the transistor. So, and this is another way to, well, basically what we usually plot for FeFET memory cell is just the point here where we go from depletion into inversion, and this is the threshold voltage. So if we go from negative to positive, we see here that we get around 1 volt. We get the high VT, we call that. This is the threshold voltage of the high conductive state. And then if we go back and sweep from positive to negative, we get the threshold voltage at a very low voltage. And this is the low conductive state. So this is the one which is usually, in this case, it's on even at 0 volts. So it conducts a lot of current. And well, if we look here in the experimental data, we can see that this going from inversion into depletion of the MOS capacitor, it doesn't happen at minus 0.6 volt. It happens actually at 3 volt. So, and usually if the threshold voltage is very high in a transistor, that means there are some traps in there or some charged electrons are in the stack. And so during this upsweep where the polarization was switching, we also trap electrons in the stack, and this shifts up the threshold voltage of the transistor to a very high voltage. All right, so now in this section we try to further look into what is really going on in this whole system if we apply these triangular pulses. And first we're going to look more into the trapping. So if we try to quantitatively say what is really the trapping that is going on, and then bring these traps into the simulation and try to figure out if this will actually stabilize the polarization. Okay, so the first thing is that, okay, this is a polarization measurement, so you measure the displacement current of the transistor, and you can also see the depletion capacitance of the transistor here in this example, but we really wanted to make sure that this depletion capacitor and that this experiment really corresponds to what we can see in an actual ferroelectric transistor over here. And so the experiment here goes as follows. You kind of put this ferroelectric transistor into a high conductive state. So this is, you apply a positive pulse, then you apply a negative pulse, and then you read it out. And if you read that out, you get this transfer characteristic of the transistor, and it's at around 1.7 volt, which is the high VT state, we call that. And then you sweep all the way up to 5 volt, and then you sweep down. And so this is the orange line, which is very bad here to see. And you can see that the VT of this transistor, it shifted up to 3 volt from 1.7 to 1.3. And then very interesting is also that if you then repeat this triangular pulse again, you don't start at the low VT state, which should be around here, but you start still at some trapped state, which is the green line here. And yeah, so it's even after the down sweep, there's still some traps there, and then it takes a while to get them out. This was Sven talking about before, so you have to wait like a second or something like that, and then also these traps come out. So there's traps that already during the down sweep, they are released, and then for the traps that are deeper into the stack, you have to wait a little bit longer. All right, so And to further quantify the trapping in these FeFETs, we made a dedicated experiment just for the trapping, and this is directly on the ferroelectric memory cell. So you apply a negative pulse and a positive pulse. So this positive pulse, it brings it directly into the low conductance state. So, and then we apply a pulse with various pulse width and pulse amplitude, and we read out the IDV, or the transfer characteristic that you saw before in this slide on the edges of this pulse. And from there we can then determine how much the threshold voltage shifted. So, and we can do this for various pulse widths and pulse amplitudes. So here we go from 1 microsecond to 1 second, or 100 milliseconds. And then we can basically see that it shifts up to 3 volt. And then Ginestra can take this data and can basically extract the trap density out of it. So this is what is shown here. So this is the band diagram. This is the silicon dioxide. This is the ferroelectric high K. And this is the amount of trapped charges. Here, this is 10 to the power 20 in this region here. So here there are no trapped charges because here there's a tunneling path out, so these states cannot be occupied. Okay, so now we kind of know the rough ballpark number on where we are with the number of traps we have in the layer. I have to say that this fitting with Ginestra, it didn't include yet any ferroelectric polarization switching. So we just assumed this layer is actually dielectric and fitted then the trapping. So because in reality this is not the case. In reality it switches and traps at the same time. So probably the number of defects is even higher. But we kind of try to figure this out by introducing now the traps into the simulation and see if we can like reproduce these ferroelectric switching peaks that we see in the sample on the experiment. So yeah, without the traps, we saw that the depolarization occurs and this very high leakages over the silicon dioxide, and we add now 3 times 10 to the power 19 per cubic centimeter on traps, and we assume we have here 2 trap levels, one upper and one lower, which could correspond to oxygen vacancies, for example, but we actually don't know what kind of traps are in there, so we just assume these, basically. All right, so this 3 times 10 to the power 19 traps, they didn't do much. You still don't see any switching peaks in this current response of the ferroelectric capacitor, or the FeFET. And so we crank it up, basically. So we crank it up to the 10 to the power 20. This is what we extracted from the charge trapping fit in Ginestra. And you can see that here there's some small peaks rising up, which yeah, looks a little bit better, but still doesn't look at all like the experiment. So we cranked it up even further to 3 times 10 to the power 20 per cubic centimeter in terms of traps. And yeah, for this trap density, one can see that here there's a switching peak here, and then this feature is actually leakage. And then here, during the downsweep, it actually goes into this depletion region. And then you have the back switching here, the back switching peak for negative voltages. So although this is not a perfect fit, it shows like that qualitatively we can actually describe with the simulation what is going on. So, and here this is the band diagram basically after this last triangular pulse. And the dots here, they are the traps. And if they are blue, then that means there is no occupation of these traps. And if they are red, then it means they are fully occupied. And yeah, so if we go one back to the lower trap density, we can see that they are all filled, these traps, but this has not much impact actually on the polarization switching. All right, and here we can see that also due to these traps, the electrons, they are charged in here and in this region, and they kind of, yeah, they introduce this hump in the band diagram, so they raise the potential. And this is actually good for ferroelectric switching because this creates a field, an additional field that is mediated by the traps that helps the ferroelectric to switch. And so this is actually beneficial for switching, and this is also what you can see here for the current response. All right, so, and then we have here the more band diagrams that show how what happens during these different steps. So we start here with the high VT. This is again the depletion capacitance, and so the ferroelectric transistor has to go into inversion before it starts to switch. And then when it switches, at this point here, this is basically the coercive voltage of the ferroelectric. You can see that there's some electrons trapping in already. And then at the second point here, which corresponds to this band diagram, the polarization is already almost fully switched, but completely overcompensated by electron traps. So you actually don't see if you read out the ferroelectric transistor in a normal way, you wouldn't see a ferroelectric memory window, you only see a charge trapping memory window. And then you kind of have to wait until these electrons come out, and then the ferroelectric memory window reveals itself. And this is actually what happens already during the downsweep in the triangular pulse. So if you go from here to here, you can see here in the band diagram and in the occupation of these traps that, well, maybe not in here, but I made a circle, so that first these electrons, they move out first because they're closer to this interface, so there's the tunneling probability from here to here is actually much lower. And these in the middle, they are kind of stuck in there, so they will need longer time to detrap. All right, so and the same thing, it also happens for the negative voltages. So we go basically from point 3 where we were before. So we apply a negative voltage, and then the silicon surface is in accumulation, and there will be holes here. And these holes, they can tunnel to these traps and charge them positively. But what is interesting here is that we can actually never quite reach these electrons that are deep in the stack, at least in terms of simulation. This is not possible, so we can never, if we do the polarization hysteresis, we can never fully recover them or make this part neutral. All right. And so if we go then to the band, we sweep further up. So now we were this part, then we sweep further up to 5. This is this band diagram. Even more electrons go into the stack, and now the polarization is fully reversed. So from a polarization point of view, we are now in the high VT state, or this is the state that doesn't conduct any current actually. Okay, and if we go back, we can see that the positive charge here is fixed because it's much more difficult for them to tunnel out from here to here, because here the band offsets are much higher. So actually for this not conductive state, there's actually no trapping effects observable because this positive charge is very stable and the polarization is also rather stable. And yeah, so we usually don't have any issues with the high VT state. Okay, and then there's what implications this has for the FeFET memory cell. So we have these traps now in the memory cell, and we kind of, to read out the FeFET properly, so you have a high conductive state and a low conductive state, we want to we want to sense that, but if we always have to wait 1 second or something like that, as Sven showed, to remove them, then it's very difficult to make a memory out of that. So we have to find ways to accelerate that. But we first wanted to try to understand what is really like going on in the stack. When Ginestra did actually a great deal for that, because it's really not so easy to understand what is going on if you just have experiments. So because the issue, this is what is done here. So you have a non-destructive threshold voltage read, and this is the threshold voltage, and this is the, we call that short-term retention, but it's basically just the wait time after the programming. You wait a certain period of time and then you read it out, and you can see that at the beginning, at 40 microseconds, the high VT and the low VT state, they are basically at the same position, and then after like 1 second, the memory window opens up, and this, from an experimental point of view, one could say, yeah, this corresponds to the electron release. But if we do now a destructive read of the polarization, we see that if we program into the low VT state, so this is the positive voltage, and then we do a destructive read of this state, we can see that depending on the wait time between this state and between setting the polarization and destroying them again, the peak state change. So for the longer the wait, the less polarization response you get. So that means actually the polarization is already relaxing in this waiting time too. So you have kind of two opposing effects that they don't quite make sense, right? So this is the electron release that should shift the VT down, and here you have a relaxation of the polarization, which should actually shift the VT up. And so, yeah, this was for us not possible to understand without Ginestra, so we did this simulation. So this is now the flat band voltage, but they have a constant shift in between. And so you have we can distinguish within the Ginestra simulation the flat band voltage and for the trapping, and the flat band voltage during the polarization. So after we programmed the cell, there are still these electrons in there, and we have the polarization. And effectively, they cancel each other out. So you have the trapping is about, the trapping VT or flat band voltage shift is around 5 volt, and the one from the polarization is also a minus 5 volts. So in sum, they are 0. But then you have this release of electrons, so the electrons, they trap out. And it seems like that over time, this release of the electrons is actually much faster than the depolarization effect. So at some point, there's this wedge structure forms, and this is because of the polarization. And this wedge structure, it pushes these traps below the Fermi energy. So these traps are now negatively charged, and you have the polarization effect, and they kind of stabilize each other. So yeah, it's very interesting that this happens like that. And then you get, if you have in this state, at least in the simulation, and also if you process it correctly, as Sven said, this has retention until 10 years. So this is 10 to the power 8 seconds. And so this is actually what we want. All right, so the issue is now that we have to we don't want to wait like, I don't know, 2 seconds or 1 second until these electrons are out. So we need to come up with some way to detrap them faster. And this is usually done like that, and Sven has shown it before. So you you program it in the state that conducts a lot of current, and then you apply with a small amplitude in negative direction, you try to suck out these electrons out of the stack, and then the normal low VT will like show up, and you can really distinguish between high VT and low VT. So we did this experiment, and we see that at 2 volt, we can see the difference, or we see the biggest difference between high VT and low VT. But you have to be really careful with this voltage. So if you increase this voltage too much, you will shift the polarization again into the high VT state. Okay, and basically to tackle this detrapping effect and also to tackle some variation you have in the cell, because not every cell in the ferroelectric is the same, so depending on the grain size and the grain orientation, you know, if you make the transistor very small, there will be some variations because the grain composition of each transistor is very different. So, yeah, to kind of tackle this, we developed an algorithm for programming into the low VT state, and so this works like that. You basically have a program pulse, and then you have a detrap pulse, and then you actually read the conductance of this transistor, and then you apply a series of increasing detrapping pulses where you always try to verify if you have at the right VT. So if you, let's say, this first pulse didn't really bring it into the low VT state, and also the detrapping won't have any effect, and then you kind of start with the next set of programming and detrapping pulses. And you always, this is important, you always verify in between, and once you are at the point where, okay, you can say, this is where the threshold voltage where I want to have my transistor, you basically stop and you don't apply any pulses. And this is very effective in basically making the transistors look like all the same. So, of course, it's better to tackle that also with the process, but that is always not as easy as just using these algorithms. Okay. So, and this is the results we get. So these are the IDVGs without algorithm, and you can basically see that both the low VT and the high VT, they shift up if you apply up to 10,000 pulses and 10,000 cycles. And yeah, this is still not clear where the origin of this effect comes from, but maybe one can think that actually this comes from accumulating even more electrons into this middle of the ferroelectric hafnium oxide, which then with every cycle charges up the transistor. And yeah, because in the simulation before for the erase pulse, we also showed that, I have to go all the way back, that we cannot actually get completely rid of all this negative charge during one program and erase cycle. So they're kind of stuck, and if you do repeated cyclings, then the charge will just, the negative charge will just accumulate, and this will lead to a shift of the threshold voltage for both high VT and low VT to more positive voltages. So with the algorithm, we will basically able to kind of fix all that, because like, okay, if it's like continuously charging up, we just will apply larger detrapping voltages. So problem solved, no? But yeah, I mean, it's very important to really understand what is like kind of, or what could be the physics behind all these experiments, right? Okay, and we are now looking basically to have a good overall fit for all the experiments we did. So we have like tons of experiments, trapping, detrapping, polarization. And so what you see now is more like a qualitative fit. So, okay, we see the ferroelectric switching peaks. We see that the VT is kind of the same, but it's not that we have a perfect fit of these of all these experiments. So we try that to do with the Ginzburg-Landau model. And Yeah, for that we also need some help in terms of simulation, because like in the Ginestra simulation, the input is basically the defect energies, the relaxation energy, and the band gaps and the band offsets, and you have actually quite a lot of parameters. So this makes it very difficult to fit all the experimental data. Okay, and but once we have a good fit, we want to try to include the ab initio defect data that was calculated for different dopant atoms, and try to predict if this will like kind of change the trapping or detrapping or the retention, or I don't know what could happen. All right, I thank you for your attention.
Thank you, Johannes. So we have time for questions.
Okay, thank you, Johannes. In the first presentation from Global Foundries, we saw that there are pool of electrons accumulating in the potential well formed by the interfacial layer and the conduction minimum of the ferroelectric. And I didn't see that in the model that you were presenting. Could you comment on that?
Yeah, so it seems, I mean, they are in the Ginestra model. I'm not sure if it's possible to see them, but so as you have seen that already during the downsweep, the traps very close to the interface in the upper trap band was already emptied. So the ones that are even further than the ones that are on the conduction band, eventually they will be out even sooner. But of course, if the wedge is formed, they will flow into the wedge, and then they can trap to these trap bands there. So it's kind of true, but there's a little bit more details to it.
Okay, so is it fair to say that they are there in Ginestra in the model, but they not detrap, they actually tunnel out very fast?
Yeah.
Okay.
Yeah.
Okay.
It's very interesting insights. I have one question concerning this single domain switching that Sven showed, where you have this steep abrupt switching things, and also from large capacitors, we know what's also in the Preisach model, that you can have different polarization states by polarizing single domains up and down, and the sum of the whole polarization gives you then the overall polarization, so to say, in the capacitance measurements or PV measurements. Now, if you say you stabilize just 2 microcoulomb per square centimeter of polarization, you mentioned this. How can one understand this? So would this be also kind of a gradual stabilization within a single domain that you assume, or is there also kind of an averaging effect?
So in the Ginestra simulation with the Preisach model, we completely polarize the ferroelectric, and then during the phase where the electrons move out, we slightly depolarize it, maybe from 15 microcoulomb to 10 microcoulomb. So there is some slight depolarization, if you will. And well, this is because we use the Preisach model where this is possible. But also within the Landau model in Ginestra, some slight depolarization is actually possible. I don't know how this really fits to the single domain switching. That is still a little bit unclear to me. But yeah.
But, so you assume that this gradual polarization would be possible then by spreading directly the traps or the charge within the whole ferroelectric, which gives then also for a single domain vertically somehow a smaller polarization. So not just 2 states anymore, as one would think from the Landau model, but then having multiple states even in a single domain.
Yeah, I mean, you don't have like infinite traps in the hafnium oxide, right? So it's not a metal. So, I mean, let's say you have a domain which is like perfectly aligned to the silicon dioxide, which has like 50 microcoulomb. I mean, you have to add actually 3 times more traps in Ginestra, which kind of, you know, then it gets like, you have a trap density where this is a conduction band, probably. So, yeah, in this case, I don't know, probably you cannot stabilize this domain, so it will probably backflip very soon, I guess. But, yeah, but this is something we actually, that can be found out with Ginestra and, you know, yeah.
Okay, thank you.
Excuse me, in your view, which are the trapping defects that are there? Which is, because it's a big number, about 10 to 20, no?
Yeah, it's actually as big, it's so big that you can actually measure it with XPS, so they're quite big, it's quite a large number. So I don't know what it is.
But this kind of trapping defects that you have are defects in the composition of the sample, and if that's the case, how the charge is compensated?
No,
I mean, you said at some point you mentioned that could be oxygen defects, that's fine. But then that means that you have basically 10 to 20 electrons in the conduction band. You have, I mean, you have hafnium, which is whatever, instead of being 4 plus, it's going to be 3 plus or whatever, no? So you have a huge number of electrons.
Yeah, so if you assume there are oxygen vacancies and they have a neutral state, right? So you can just assume they are neutral, no? At the beginning. And then they can charge up if you operate the device. So because this is also the usual defect that you assume in a high-K metal gate. So you have an oxygen vacancy, which is like not charged. And then if you apply for a long time some voltage, you charge them either positive or negative. But there could be also different, you know, depending on the dopant that is in there, which I cannot disclose, could be, you know, could be a different defect, and then your question is actually very valid. So,
and these kind of defects, do they have any impact in the transport properties of the layer itself? If you measure, I don't know, the conductance, the Hall effect, the photoluminescence, how you can control this number? Is there any way to cross-check that?
So you could probably measure with photoelectron spectroscopy or some other method, right? But this is actually, I don't think this has been done for this specific ferroelectric material that we're characterizing. But there are some studies out there where they did that also on doped hafnium oxide, where they also have trap densities in this area.
Okay, thank you.
So I have also a question related to this trap origin. So you mentioned that you have traps with, let's say, a few traps are faster than others, let's say in this way. So for the fastest one, so how fast they are? In the sense that, do you expect that at the microscopic level, this is associated in any case to a reoptimization of the structure? That again means that you have localization, possibly of the charge locally, or is too fast that you don't have any, let's say, structural effects?
I don't know.
Okay. Yeah. Are there any other questions on this? If not, so let's thanks Johannes again.